Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Okay, and moving right along. You're here to hear about the Large Hadron Collider at CERN, and this is the largest particle collider ever built, and the collaborative project of I don't know how many nations, dozens of nations, and hundreds of institutions, and thousands of physicists and engineers. It's been called the greatest machine ever built. And the project itself is an enormous cooperative international project for once not a war. And great minds think alike, evidently, to make this project work. The mission is to reveal the most fundamental components and forces of our universe, which were produced originally in the earliest milliseconds of the Big Bang. These objects gave rise, of course, to the forces of nature and to mass and subsequently matter, which has made you and me. We're very fortunate to have as our speaker tonight an expert on these fundamentals and a major participant in one of the major experiments at the LHC, Dr. Stephen Nahn, an associate professor at the Department of Physics at MIT. Dr. Nahn received his PhD from MIT, and for those in the know about these things, it was for the analysis of the W boson pair production, and he worked with some very famous people there. After receiving his PhD, he went on to Yale as a research scientist, and he was involved in the collider detector at Fermilab in Illinois, and then went back after that to MIT. Now he's concerned with the one of the two biggest projects or experiments at the LHC in CERN, the compact muon solenoid. His research interests aim for an understanding of the mass and potential extensions to the subatomic periodic table. I like that term. Dr. Nahn has just come back from CERN this week. He missed the snow and will describe for us the goals and the complexity of the LHC, his own work there, and the state of knowledge now after the first year's running that many of us were waiting for all our lives, okay? Very generous welcome to Dr. Stephen Nahn.
Thanks very much, and thanks everybody for coming out tonight. I know there's another speech going on in DC a little later on, so I'll try to be quick so we can all hear that one as well. What you're looking at here is a visualization, of an ion-ion collision, an actual ion-ion collision as seen in our detector. And so there's tons and tons of particles going all over the place, leaving energy depositions and tracks and such. It's a big bang indeed. What I'll try to do tonight is to tell you why we are interested in these kind of events and exploring this kind of physics, how we actually do this, and what you might be able to expect in the next year, what we found already and what you might be able to expect in the next year in terms of discovery. But before I do that, I should tell you who we are, right? So this was mentioned already. What you're looking at is the author list for one of the recent papers that my collaboration put out. There are 2,000 names on there. In the 2,000 names, actually the ones in yellow are the ones from the US institutions. I am right down here in green, but you probably can't see me. Right, so we are a huge collaboration. This is not my work, this is our work. And when I say our work, I mean quite a few people that go into making this kind of big physics actually work out. Of local interest, there are 8 institutions in sort of the 50-mile radius that all participate in this kind of physics at the LHC. some on my collaboration, some on the other collaborations, some on both. And finally, actually, none of this would be possible without you, because all of this research is funded through the auspices of the National Science Foundation and the Department of Energy's Office of Science, and they get their money from taxpayers. So let me take this opportunity to thank you for allowing me to go do this kind of work. Okay, so what is this kind of work? So my kids here tell me that with the appropriate building blocks, you can build almost anything, including Sacré-Cœur. Of course, their appropriate building blocks are Legos. Nature doesn't use Legos to build things. What nature uses is much simpler, actually. It's these 12 objects here. These are the fundamental building blocks of nature. And it's a little complicated, so I'll walk you through them. But really, what there are 3 generations. And each generation has a pair of leptons. These are the green things down here. The electron you're probably familiar with. It has a neutral, electrically neutral brother called the neutrino. And then there's another pair up here called quarks. There's an up quark and a down quark. And this pattern repeats 3 times, once for each generation. As you move up in generations, the particles get heavier. So there are these 12 things, and they're associated antiparticles, and that's it. And out of those things, we build everything else that we know of in the universe. Now, just having a bunch of stuff laying around is not all that interesting unless you know how to interact, how they interact. So we also study how they interact. And the way we talk about interactions, sorry, wrong button. Oh, maybe the right button, there we go. We talk about them in terms of their force carriers. So there are 3 kinds of forces which are relevant for subatomic particle physics. Gravity is the odd one out. For gravity, you need objects the size of planets to be able to feel them, right? So these things are very small, so gravity doesn't really play a role. However, the electromagnetic force plays a role, and that force carrier is the photon here, and interacts with all the charged particles. So all these quarks up here are charged, and these these leptons down here, the electron, muon, and tau, are also charged. The neutrinos are not. And electromagnetism, we know a lot about. Everything in the room right now is using electromagnetism to power it and that sort of thing. Then there's this gluon here. The gluon is just like the photon, except it doesn't interact with electric charge. Interacts with what's known as color charge. Color is the charge of the strong force. The strong force is what holds the nucleus together. You have a bunch of protons and neutrons in a nucleus. They'd fly apart if it weren't for the strong force. So the gluon interacts with this color charge, but the only things that have color charge are the quarks. The leptons do not talk to the gluon. That's actually what separates quarks from leptons. Finally, there are these 2 force carriers down here. These are the 2 force carriers for the weak force. Weak force is responsible for certain nuclear decays and that sort of thing. The weak force talks to all of the particles, including the neutrinos. So they're the most democratic of the forces, if you like. They're also strange in the sense that whereas the photon and the gluon have no discernible mass, these guys are actually very heavy, heavier than almost everything in the chart except for the top quark. And that causes problems for the theories we use to describe these particles, which I'll get into later on. But that's basically it. So now we have a bunch of stuff. We know how the stuff interacts. We can build a universe. You might ask, how am I so confident about this, right? And I'm confident about this because I'm an experimentalist, and we do experiments with accelerators. So some of the things that we found out about this whole periodic table, subatomic periodic table, first of all, in the 60s at Stanford, we found out that the proton is actually not a point particle itself. It is made of 2 up quarks and a down quark. Likewise, the neutron is made of 2 down quarks and an up quark. So it's just like Legos. You're just putting them together, different combinations, and you make the rest of the particles, you know. In the 70s, we started to learn that there are more than just 3 quarks. By then we knew something about the strange quark, but we didn't know much about it. We thought it was strange, right? But we discovered this charm quark in the 70s. And that was really important because as soon as you have 4 instead of 3 objects, you can start making 2 pairs and start pairing them up with this and start understanding what the structure really is here, right? The process of discovering the quarks ended in the 1990s with, the charm quark was discovered simultaneously at Brookhaven and at Stanford. The top quark in the 1990s was discovered at the Tevatron at Fermilab, and that sort of ended the, filling out this part of the periodic table of the subatomic elements, right? In between there there was accelerators both over in Switzerland and again back at Stanford that were able to produce Z bosons and W bosons, these heavy, weak bosons, in copious amounts. And not only did we understand what that was all about, that there really exist these Z and W massive force carriers, but we also were able to study all of these particles because they couple to all of these particles. So this was in between, say, the 70s and the 90s. We learned a lot about the electroweak nature of all of these particles. And more recently, there was accelerators both in Japan and again at Stanford, where they produced copious amounts of B mesons and B quarks and anti-B quarks, and studied the differences between antiparticles and particles. So out of all of this, what you should take away is that accelerators are very useful, and they're what really taught us what was going on with this subatomic table. So what next? So when I came to MIT about 5 years ago, my first idea was, hey, we need an accelerator here, right? And we have all these, we must have equipment lying around from the big dig, so we could put a nice accelerator right centered around my house, and I wouldn't have to travel so much. It would be great. It's a shovel-ready project. But then I thought a little bit about how much funding I had, and a little bit about the sort of shortcomings of schedule and cost overrun with the big dig, and I thought there's a better idea, right? More popular these days than doing something like this would, of course, being green and recycling. So we recycled an old tunnel over in Geneva, Switzerland. So this is Lac Léman, those are the Alps, Mont Blanc is there, and this is Geneva in here. And it's a 27-kilometer circumference ring that was used to collide electrons and positrons, and now we collide protons and protons in it. So what it looks like underneath, this device is not working very well. It's something like this. Anywhere between 60 to 120 meters in the ground is the tunnel, and in the tunnel you send protons in one direction and protons in the other direction, and they collide at any of these 4 interaction points where you put detectors and try to see what happens when they collide. Initially, we wanted to do 1 million events per second at 7 tera electron volts, and eventually we want to get to 1 billion events per second at twice the energy, 14 tera electron volts. These would be the highest energy collisions ever produced. In addition, we can do lead ions at a slightly less energy, but that's per nucleon. So they have a whole lead ion program, but I'm not going to talk too much more about that. So that's the idea. This is what's going on over at the LHC. Why is it such a big deal? So here, what I did is I plotted on this funny plot. So it's a logarithmic plot in this direction. This is the energy of the beam in some units called giga-electron volts, 10, 100, and 1,000. And this is what's known as the luminosity. But these are kind of funny things, right? So you can think of it as you go up in energy, you have more chance of making heavier things. And as you go up in luminosity, you have more chance of making rare things, right? So luminosity tells you kind of what your event rate is going to be. If you're looking for a process that happens 1 in a billion times, and you get 1 billion events per year, you're going to see that once. If you get 10 billion events per year, you're going to see it 10 times, and so on and so forth. So as you go up in this way, you're more sensitive to rare things. As you go out in this direction, you're more sensitive to heavy things. If you simply don't have the energy to make a very massive object, you're not going to see it at all. These are the 2 ways that you can miss discovering something, right? So here are a bunch of the accelerators that I was mentioning in the previous slide and where they sit on this plot. And then the LHC is way up over here in this corner. So it's basically an order of magnitude over in energy and 2 orders of magnitude up in luminosity. So it's a huge opportunity to be able to discover something new. And that's why it's the most important feature in the high energy physics world. Okay, so what is this business about the Big Bang? Why is Big Bang in the title of this? So this is a cartoon of the evolution of our universe back to somewhere around here, 10 to the minus 10 seconds, which is about as far back as we can actually accurately figure out what was going on. What you see is there was this strange Big Bang and then some inflation here, and the universe started to grow. It was very hot and very dense in the beginning, and as it grew, it expanded and it cooled down. Right? And so at some point in here, it was hot enough that you had basically a soup of all of those particles just floating around. They had so much energy that nothing stuck together. You didn't get any kind of bound states or anything. It's just a soup of particles. As things cooled down, you started to form bound states of Q and Q anti-quark and anti-quark pairs. Those are mesons. And 3 quarks altogether, that makes a hadron, like a proton. And you still had electrons flying around and then these bound states of quarks flying. Then at about 3 times 10 to the 5 years, you started to get ions, so the quarks started, the the hadrons started binding together to make ions. The electrons were still floating around. Somewhere out here in 10 to the 9 years, you started to actually make atoms, where the electrons joined up with the nuclei and formed atoms. And then out here, 13 billion years later, is today. So the point is that the energy that you get in these collisions produces in a very small volume the same environment that was going on back here, the same sort of temperature and energy density going back here. So if we produce these collisions in the lab, it's like in a very small way we're sampling the physics of this period in the early universe. And that is why we consider this a Big Bang machine. Okay, so what are some of the hot topics at the LHC? First of all, I have to do a little bit of physics, talk a little bit about what is mass. So most people think they have a fairly good idea of what mass is. And most people usually think of what Mr. Newton thought of at first, that mass is the ratio of the force over acceleration. So, mass is the sort of constant that tells you if I push on something really hard, how fast does it start moving, right? If it's massive, it doesn't start moving very fast. If it's not very massive, it starts moving right away, right? That's sort of the macroscopic definition of mass. Another definition of mass, which when in the morning you step on your scale and you look down and it tells you something about how much you weigh. So there's a gravitational role in mass as well. It's essentially the charge of gravity. If you're standing on the Earth, Earth has a big mass, capital M, and you're a distance r away from the center of the Earth, then you feel a force on you that goes like some constant times your mass times Earth's mass divided by the distance between you and the Earth's center squared, right? So surprisingly enough, if you just take those two equations and you equate them, you find that your acceleration on Earth is a constant, because the little m, that m there and that m there, they cancel, right? The fact that they cancel is accidental. No one really knows why, so we call it the equivalence principle, that these two masses are the same. And this is what Mr. Galileo told you when he dropped things off the Tower of Pisa, that different objects with different mass accelerate at the same rate. That's what that's telling you. And then the third definition of mass came from our friend Albert, right? So the mass here is the energy of a stationary object. Everybody thinks they know this equation. They actually don't. The real equation is the energy equals the square root of mc squared quantity squared plus the momentum times c quantity squared. However, if I take a stationary object, what happens is I get to get rid of that momentum, like that, and that goes to 0. And so then I have the famous equation E equals mc squared. And this is the mass that we're really talking about. So this definition of mass, and we're looking at the mass of these fundamental particles. So why is this a hot topic? You remember the periodic table, subatomic periodic table, and how it was all neat and orderly, and you had 3 generations of 2 pairs apiece and all that. So this is a plot of the mass of the quarks, where the font size is proportional to the mass. So you see, here's the up quark. You can't even see the U where the little green dot is. The down quark is twice as heavy. You still can't see it. It's only when you get up to the charm quark that you can actually start to see the font. And then the top quark is huge. There's a difference of like 30,000 between these two. So why is there this huge disparity in mass when everything else seems to fall nice into the nice little boxes and stuff? Not only that, but there's a deeper problem. And the problem is in the model that we use to explain all this stuff, which has been extremely successful for 30 years, there's no room for mass. All of these things should be massless. And if they aren't massless, if you put in mass in a naive way, what happens is you start making predictions of probabilities that are bigger than 100%. And that's not a good theory. No probability should be bigger than 100%. That's called breaking unitarity. So you got to come up with a tricky way of inserting mass into these equations that describe all these fundamental particles, and yet keeping the theory consistent. And so the simplest way to do this was thought up by a guy named Higgs. And it's thought up by others too, but they didn't have as good a publicist as Higgs does. So it's called the Higgs mechanism. And it's basically an economical way to have a consistent theory, but also have non-zero particle mass. This also holds true for those W and Z bosons I was talking about before. Right? So that's what the Higgs mechanism is. It just is a way to give these particles mass where otherwise the theory wouldn't be right. And the theory has been tested and tested and tested. It clearly has predictive power. So it must be right on some level. We just need to fix it up. That's what the Higgs mechanism is. It's economical because it only requires you to invent one new particle between 114 GeV. That's because we searched for it up to that point and didn't find it. So that's the lower limit. And 1,000 GeV. It's because if it's heavier than 1,000 GeV, then the theory breaks down again. and we don't have predictive power. So the reason these two numbers are important is because for the first time, the LHC has the reach to cover this entire range. So this is some sort of guarantee that we should be able to answer whether this simple Higgs mechanism is the mechanism that endows the particles with mass or not at the LHC. And that's why this is so exciting. Finally, we get to settle this once for all. It might be something much more complicated, but at least we can knock this one off the table or prove that it's right. What other topics are there? Well, there's another problem, and this one is kind of embarrassing, right? So this pie chart here is a pie chart showing you the energy density of the universe broken up into several components. The smallest component here is all the stuff we see our visible world, and it's at about 4%. So what is the other 96% of the world? Right? I just told you we have this beautiful model, predicts all this stuff, and we don't know what 96% of the energy density of the world is. That's crazy. 73% of it is wrapped up in this term called dark energy. Nobody really knows much about dark energy other than it's dark, which means we don't see light coming from it. It doesn't interact electromagnetically, and it doesn't seem to interact gravitationally. So it's energy, as opposed to this 23% dark matter. Yeah, I got those numbers right. Okay, dark matter. Dark matter is also dark. It doesn't interact electromagnetically, but it does interact gravitationally. And we know this by looking at effects like gravitational lensing effects or the rotation of galaxies way out in our cluster, that sort of thing, tell us that there must be something else out there that interacts gravitationally. So most of that information comes from astrophysics. What does this have to do with the LHC? At the LHC, we have a possibility of seeing new particles, new heavier particles, and it could be that one of those particles, the next new particle, is a good candidate for representing this dark matter component of the energy density of the universe. So maybe at the LHC, if we can produce some of these and observe them in the lab, we get to beat the astrophysicists to the punch and say, we know what dark matter is. It's this new particle that we produced. And it has a couple other side effects as well. In some theories that propose that we know what the new dark matter candidate might be, you can also do things like unify the strong and electro-weak forces. And you can also cure further theoretical ailments, like the breaking of unitarity that I talked about before. That happens at a yet higher energy scale, but you can actually cure those problems as well. And who knows, maybe you can save the economy. Some of these theories, it's like the theoretical physics Leatherman. It does all sorts of things, had all sorts of tools in its pocket. So anyway, this one, however, when you invent new theories like this, they come along with a whole bunch of parameters. So the problem here is you can always tune those theoretical parameters to escape the experimental reach, right? So here I can't say a guarantee. I can say a possibility. Maybe the dark matter candidate is within the LHC reach. Finally, the other hot topic you would say is this all there is, right? I have this really nice table of 12 matter particles. These are called fermions because they're spin 1/2, and the force carriers are called bosons because they're spin 1 particles. Is that it? Maybe there's another generation. Maybe it doesn't stop at 3, it goes up to 4, and we just haven't seen it yet. Maybe there's additional force carriers. Maybe these Z's or W's. And some theories actually invent an extra dimension or two. And certain particles like these Z's and W's can travel in an extra dimension. To us, that would just look like a heavier Z or a heavier W. Maybe that's the case. Maybe there's substructure. Right? Maybe the bottom quark is actually made out of a few things, or the quarks in general, just like the proton is made out of quarks. And we simply don't have the energy reach to excite those substructure features and be able to see heavier quarks, for instance. Or maybe there's a strange thing that the force carriers are bosons and the matter particles are fermions. There's a theory called supersymmetry which says, well, there are matter particles that are bosons and force carriers that are fermions. It just switches the two. And this is actually probably the leading theory that explains the dark matter problem I was talking about before. That there's a whole nother mirror that flips fermions and bosons back and forth. And finally, and the most important one, and frankly the one that the physicists are hoping for the most, is that we haven't even thought of what we're going to find. Because when you have a surprise like that, if you have a theory all laid out and you just find that theory, and you already know everything about it. It's rather boring, actually. But if you are surprised and you have no clue what's going on, that's when you learn the most. So that's really, at least in my opinion, would be the best turnout for the LHC. All right. So where is the physics? How do we actually get at this? So I have a chart here. What the chart is showing you, it's kind of crazy, but it's basically the relative production rate. So this is one. If you get one of these, you get 1,000 of these, 1,000,000 of these, 1,000,000,000 of these, 1,000,000,000,000 of these, right? And the blue things are processes that we know where they are. So it's the relative production rate versus the mass of the thing that you're trying to produce. So the blue things, we know where their masses are. So they're just points. There's the W boson production and Z boson production. There's certain decays to leptons, for instance. There's top, anti-top production. Up here is actually production of any single event, right? Now the colored stuff down here, the red and the magenta and the purple, are all hypothetical things. Like the Higgs boson production is all down here in the red. Supersymmetry is over here in the purple, and excited Z bosons are over here in the magenta. I guess you can't really see the colors. But the point is, say let's take a typical process that we're looking for, like a Higgs decaying to 2 Z bosons, which goes to 4 leptons. And say the Higgs is 200 GeV, so that's this line. So that means I get about 10 of them, but I get in 10 trillion events, right? And this is why it takes so long, because for every Higgs I get 1 trillion events. I have to make sure that each one of those trillion events doesn't fake the signature that I'm looking for with a Higgs. So if I wait and I only have 10 events, I really can't be sure, no matter how good my filter is, I really can't be sure that none of the 10 trillion got through that filter. I need to see like 100 or 1,000 events, and then I can be more sure that my filter is really working and that my signal is really truly a signal and not this mountain of background that sits above my signal. So that's why we have to basically dig through the standard model to be able to get at these new processes. And that's why it takes a while for us to actually get results. So stop holding your breath. Okay, how do we actually do these things? Let me tell you a little bit about the accelerator, and I'm going to pick it up a little bit because I have to move along. How do you move a particle in a circle? So you use electromagnetism. There's 2 components to electromagnetism. You can accelerate it with an electric field. That changes the momentum, right? As you accelerate, you change your momentum. To get it to go in a circle, perhaps less familiar to people, is that you can actually bend it with a magnetic field. That's this B is this magnetic field. So depending on how much momentum it has, it will bend in a circle. It won't change its momentum. It'll just change its direction, right? And this is the thing that gives you circular motion, right? So this is the force. This is the equation for circular motion. I won't go into details, but a simple calculation shows you that the amount of momentum you have is proportional to the charge you have, the size of your magnetic field, and the radius of curvature. And if you don't believe me, maybe you remember when you were a kid and you had an old TV and you took a magnet up to your TV, you could actually deflect the image and distort the image with a magnet just pointing at your TV because the electrons were coming out at your TV, and you put a magnet there and you bent the electrons around, and that's what that picture is. I did this when I was a kid. Parents didn't like it, but I did it anyway. So what's the take-home message here? First of all, we're trying to increase the energy by applying a magnetic field or increasing the momentum. So you have to ramp up the magnetic field at the same time to keep it in the same fixed radius. So if you have a fixed radius, you better be able to turn up your magnets as you turn up your energy. More importantly, in order to maximize the energy, maximize the momentum, you need a really big magnetic field and you need a really big radius. And this is why we have these large storage rings, right? So like the LHC. So this is a picture from the LHC tunnel. It's part of a straight section and then going into a bending section. Right? It's 27 kilometers around. That's very big for a tunnel. And it has these blue things are all the magnetic pieces that go all the way around and guide the beams all the way around. Right? This is the heart of the LHC and what makes it work. These are these superconducting double dipoles. So you can't really see them here, but these are superconducting coils. This is superconducting coils here because you have the same particle going in opposite directions. You need 2 of them, one with the B field pointing one way, and the other with the magnetic field pointing the other way. And if you just do a quick calculation, which I won't really go through, you find out that these magnets need to be about 8 Tesla, which is about 100,000 times the magnetic field of the Earth, and the biggest magnets you can make. Actually, you can get twice or 3 times that magnet, but you can't make 1,200 of them and lay them around a ring 27 kilometers around. All right. And the beauty of this is actually they use the same sort of environmental control for both of the beams. And both of the magnets. This is this 15-meter long LHC cryodipole. So inside the beam lines here, there's a vacuum that has less particle density than outer space. And they surrounded the beam lines and all the superconducting magnets in a liquid helium bath That's at 1.9 degree Kelvin. That's also colder than outer space. So doing this is the key to making the LHC work, giving it the highest energy and the best luminosity of any accelerator out there. And it certainly pushes the frontiers of this kind of science on many different fronts. All right, the other thing I should talk about a little bit is the energy stored in the beam. So there's nothing more to say about it than it's just enormous, right? The beams store about 700 megajoules, which is the same amount of energy that's released by 2 battleship guns going off, right? So this isn't dangerous to people because nobody is down in the tunnel when the beam is going around. However, it is dangerous to your equipment that you put down there, so you want to be very careful when you're using this beam at full strength. All right, so in 2008 we had a rain delay, and I thought I'd explain that a little bit. Everything was going great on September 10th, 2008. Google even put us on the web page, on the front page. This is partially because, I'm going to back up and see if we started circulating single beams of protons at the injection energy, 450 GeV. We hadn't accelerated them yet, but we were circulating them, and it went very well. But more likely, it's because Eurovision estimated that the integrated viewership was 1 billion. Even if they're wrong by a factor of 1,000, that's still more people than ever paid attention to particle physics before, I guarantee you. And this is probably because they were waiting for the world to end, and it didn't. So, things were going really well. The next day, things were looking good. So what I'm showing you here, this is basically a snapshot of where the beam is. It's a 25 nanosecond snapshot, and they take a snapshot every 10 turns, and then they pile them up on each other. So at 9:20 in the evening, they started to put the beam in, and without trying to accelerate it and trying to gather it together, it basically dissipated in 25 times 10 turns, so it went away. And then they started putting in some electric field to map the beam out, and at first they put the electric field in the wrong phase. And so what happens is the guys that arrive a little early get accelerated, the guys that arrive a little late get decelerated, and the beam splits in half and then dissipates. You can see, these guys are getting there early, these guys are getting there late. So then a little bit later, they put it in a corrected phase, but it still kind of wandered off. So they had to make one more final tune, and finally, they got it at the optimal phase, and you see that they contained the beam all the way along. And finally, took them 23 minutes. Usually you schedule days or weeks for this sort of thing. So when I say things are looking good, things were looking really good, right? But they had a little problem. So at MIT, we teach all students what happens when you break an inductive circuit. I have an inductive circuit here where I have a switch, a power supply connected to the switch, which goes through a little resistor, and then through these magnets. I'm going to charge up the magnets, and then I'm going to break the circuit. So charge up the magnets, break the circuit. Magnets don't like it when you break the circuit, and you get a big arc somewhere, right? This, the details of it are sort of, whoops, I was going to play again. Oh, want to see it again? Okay, good. Okay, now let's see if I can do this right. Okay, so this guy released about 3,600 kilojoules. If you convert that to what happened in the LHC, you get 680 megajoules. So that's a factor of a couple 100,000 there in terms of energy released. That's a big arc. It basically vaporized the connection, and what more it did is it broke the liquid helium, which was in a vacuum at 1.9 K, and it went out into the insulation vacuum, which is at room temperature. So suddenly the helium starts expanding rapidly, turning into gas, and you get a big pressure buildup. The relief valves basically were overwhelmed, and you had 30 tons of pressure on these vacuum barriers, and it moved equipment that weighs tons by an order of meters. Here's before, and here's after, right? So that's basically what happened. Yeah, not too good. So we spent a year doing repairs and improvements in how we react to these things until November 2009. And then, to make a long story short, in November 20th of 2009, we started turning things on. Things went very well. About 3 days later, we were colliding beams, 2 out of 2,000 buckets of protons. So, like I was saying, keeping the intensity down. You think if you're aiming a fire hose at a target, you want to turn it on just a little bit, make sure you're aiming correctly before you open it up. A week later, they ramped the beams to the highest energy ever, 1.18 TeV. 1 week after that, we were doing 4-on-4 collisions, but back at injection energy. And then about a week after that, we were actually colliding at this highest energy ever. And then 4 days, we turned off until February. Okay, that was 2009. I'll tell you about 2010 in a little bit. First, I'm going to talk a little bit about a detector. What do we do? How do we build detectors? What are detectors? So a detector, conceptually, is like, imagine having many cameras, each with a different filter on them, taking a picture of the same event, right? So this is Tim the beaver, and you see he has a yellow filter, and a cyan filter, and a magenta filter, and a purple filter, and a red filter, and each of these pick out some different aspect of Tim. Right? So our detectors are the same thing, but they don't look at different colors of light. They look at different aspects of the event, like what the muons are doing in it, or what the tracks are doing in it, the charged tracks that are left behind, or what energy depositions do the electrons leave behind. They look at all these different kind of sub-detectors inside a detector that all look at the same event at the same time. They're kind of fancy, though. So they have about 100 megapixels, if you like, if you use a camera analogy, right? And a 40 megahertz, so once every 25 nanoseconds shutter speed. So you put those things together and you get 500 gigabyte per second of data that you're producing. That's like a hard disk every second, right? A good hard disk, 500 gigabytes. So you clearly can't actually write all that to disk. So there's also a very fancy real-time filtering system in here that holds onto an event for a little bit, decides whether it's worth keeping or not, and then throws out and keeps only one out of every 10,000 events. You can imagine it's all quite complicated. Right? But that's what our detector does. What we're after, so we're after basically mass, right? If you measure energy and you measure momentum, you can get the mass of the particle. Furthermore, if particles that decay, they decay into some set of daughter particles. But since energy and momentum conserved, you can look at the daughter particles and you can reconstruct the mass and the energy of the parent particle. So that's basically what our detectors do, and they do it in a variety of different ways for different particles. Right? These are what the detectors look like for the 4 experiments at the LHC. This is the Atlas detector. Here you can't even see the person because this is not to scale. This thing is considerably bigger than that thing. Here's the person here. There's the detector I'm going to talk about, CMS. There's the ALICE detector, which is special for heavy ions, and the LHC B detector, which is special for studying B physics. But I'm going to focus on this one today because that's the one that I know the best. Right? Just for scale, do you know where you are? So this is Lobby 10 at MIT. And this is, in fact, the scale of this detector. It would fit nicely, just barely, inside Lobby 10, just to give you an idea how big they are. The dome would be up here, but somehow I cut it out of the picture. So in a nutshell, basically what you have is a series of detectors, each designed to look at different parts, and they're all sort of layered together like an onion. So it's like you're peeling layers. There's a big magnet here. In fact, it's a magnet that's 3.8 Tesla, Earth times 40,000, Earth field times 40,000. And that's used to bend the particles, because if you bend the particles, you can get a handle on their momentum. And the whole thing weighs about 14.5 kilotons. Its diameter is 15 meters, and its length is 22 meters. So you start with an empty cavern that looks like this, and then each of those pieces, you saw it was sectioned out. Those are actual sections of the detector. It's not just a cutaway. That's actually how it's built. You lower down each of those pieces until you get, and then this is the big magnet piece that comes down. And then you put the detectors that go inside the magnet in the magnet, and you button it all up, and that's what it looks like in the end. Why is it called compact? It's called compact because, like I said, our Atlas competitors, they're even bigger than we are. However, they're lighter than we are because they don't have all this red iron in there. So we're very dense compared to them. Anyway, people often ask. So this is a little cartoon of basically giving you the idea that different kinds of particles react differently in these different detectors. So I'm going to talk about the tracker, the calorimeters, and the muon chambers. So the principle of particle tracking is just like how you figure out where the planes went when you look up in the sky, right? You follow their contrails. So a tracker does the same thing. You basically follow the charged particle contrail. So a charged particle goes through some material, it ionizes a little bit and leaves a little bit of charge floating around. You collect that charge, you can figure out where the charged particle went. So this is the CMS tracking detector. It's the one that I actually work on. It's 220 square meters of silicon wafers. This is like laying out a swimming pool covered in silicon wafers. And it measures this ionization contrail. So you can see there's an inner part for very high resolution. There's barrels and end caps, so you're trying to make sort of concentric circles to try to get as many different depositions of energy along your track as you can. How you really build these things is you start with a module here, which is the 2 pieces of silicon. You add on some fancy electronics to handle the power and the data acquisition. Then you put them all together in some sort of module, and then you put all the modules together and you end up with something that looks like this. So this is the inner barrel of our silicon detector. You can see all the silicon wafers laid out over there. And this is kind of how it gets put together. So I came in 2005, and and this is just the support structure for the outer barrel of the tracker. And I noticed that I could actually walk into that thing. Now the reason that's relevant is I'm as big as the previous largest silicon detector ever used in particle physics. So what struck me is that you could take this big silicon detector, you could turn it the wrong way, and you could still fit it inside this new silicon detector. That's sort of the scale that we're going up to when we talk about LHC technology. So a year later, we were actually starting to put together the outer barrel and the inner barrel, and then we put the outer barrel inside the support tube. And then for Christmas, we got to put the inner barrel inside the outer barrel inside the support tube. At about the same time, the end caps started showing up. And then we put them in by February. By March, we were done assembling the whole tracker in about 6 months or so. We had a certain amount of time to actually test it in the assembly lab before we had to pack it all up and wrap up the cabling, which looks like everybody wants to stick a big fork in this picture, right? It looks like a bunch of spaghetti. And then Christmas the following year, we actually were able to install it. That's the silicon detector going inside the CMS detector. And then this is a simplified version of the output that you get. So these are actual particle collisions. These are actual, the little dots are the hits you see in your silicon detector, and the lines are the circular sections that we fit through them to make tracks. And so by telling how much a track bent in a fixed magnetic field, you can get at its momentum for all charged particles. So then you move outward in the detector and you have the calorimeters. So this is kind of the picture of calorimetry. The idea here, these are pictures from Doc Edgerton, right, who fires bullets into apples. And the idea behind calorimetry is, depending on how much stuff comes out, you can learn something about the particle that went in, its energy, for instance. If you had more energy, maybe you get more stuff coming out. That's basically how a calorimeter works. You have a particle coming in of a certain energy. When it comes in, it actually pair produces, and you have two particles, and those particles pair produce, and the final particles, and you get a whole jet of particles coming into your calorimeter. And as long as you catch all of them, and you put some sort of detectors in there to count how many particles went along as the shower developed, you can get at the energy of that initial particle. Right? So we have two kinds of calorimeters, an electromagnetic calorimeter that measures electrons and photons, and it's made of lead tungstenate crystals. They weigh about 3 pounds, even though they're only about this big. And we have 75,000 of them. We also have a hadronic calorimeter. This is made of brass and scintillator sandwiches. So you have sort of the brass is the bread and the scintillator is the sandwich, or is the jam, I guess. And these scintillators have optical fibers that read into photodiodes down here. And you can see, so this is the tracker, this is the electromagnetic calorimeter, the blue is the hadronic calorimeter that's trying to catch all the particles that come out of the interaction. They have inside the magnet and also outside the magnet. And out here are muon chambers, which I'll get to in a minute. So this is essentially that jam that I was talking about. This is a scintillator. A particle will come through, produce scintillation light. It'll be caught in these fibers and piped out to read out outside. That's what it looks like. This is the hadron calorimeter being inserted into the magnet there. The interesting thing about the hadronic calorimeter is actually the brass is from Russia, and they didn't have enough money to pay for it, so what they did is they recycled cartridges, brass cartridges from their Cold War weapons arsenal, and they turned it into calorimeters. So, it's just kind of a neat feature of CMS. Out here are the muon chambers, and I'll talk about them next. A muon chamber, how does a muon chamber work? A muon chamber is like a bar. How could it be like a bar, you're asking me? So a bar, you go into a bar and everybody in the bar is 21 or older, right? Because you can't get into a bar unless you're older than 21, right? So a muon chamber is the same way. You can't make it into a muon chamber unless you're a muon because you'll be eaten by the calorimeters before you get there. So a muon chamber is really about particle ID. Muon chambers are also tracking devices, typically of lesser resolution than the inner tracker that I talked about before. On the other hand, I should mention that the ATLAS collaboration is especially good at muon chambers because there's this Boston Muon Consortium, a bunch of colleagues, not in my collaboration, but in the other collaboration that were responsible for the ATLAS. So if you're out there somewhere, I hope you see that. Okay. So here's an example of a muon event, 2 muons actually. You can see here's the inner tracker and the calorimeter where most of the stuff are going on, but then you have hits out here. These 2 guys are muons, and they link nicely back to tracks found in the tracker, and that's how a muon chamber works. Okay, so and here's a bunch of events that were taken actually very early on in the running, and you can see this is basically the kind of visualization you get. You don't actually use these to do analysis. You actually sift through the data offline and do analysis that way, but that's the idea. Okay, so now I'm ready to go on to the 2010 run. Doing okay. So what happened basically is, they fell down and they got back up in 2009, but they walked fairly slowly before they really started running again. And you can see that in this chart here. This chart is showing you the total integrated amount of data we got as a function of date. So they actually started in the very beginning of April, but you can't even see this line rise. Can't really see it rise until, I don't know, July something or something. We start to pick up some data. And in August 8, so that's August 8, so somewhere towards the end of August, we collected this much data. They had a fairly long shutdown, 3 weeks or so, to make improvements based on the running here. And then they cranked up the rate. And you can see the rate went considerably up. They had another very short shutdown, and they doubled the amount of particles in the beam again, and the rate went sky high. Right? So this is looking very good for us in the future. We got about 40 inverse picobarns, which doesn't really mean anything to anybody here, but what it means is we're sensitive to physics sort of at this line and above. So the things we can do with this is we can study all these standard model particles that we know about to make sure our detector is working well. And we can also look around here to see if there's anything at higher mass, but that has high production rate, to see if there's anything out there that maybe we couldn't produce before at the lower energy accelerators. And as far as the future goes, in 2011, we expect to get somewhere between 20 to 100 times more data than we've received so far. And then in 2012, we expect to be able to double that again. So, even though we had this sort of slow start by my standards, things look very good for the future. And in fact, there's a meeting going on right now in Geneva to decide exactly how we're going to run this year and how much we expect to get. All right, so rediscovering the standard model. So the idea here is you take your known physics and you benchmark your performance. And one example of doing this is dilepton masses. So I said you can reproduce the mass of a mother particle from its 2 daughter particles. So you can look for particles which decay to either 2 electrons or 2 muons. And so here's the spectrum as a function of mass. And you see mostly it's flat or it's sort of curved down. But there are these peaks. These peaks correspond to particles that decay to 2 electrons. So you have the J psi, that's the discovery of the charm quark, there's a Nobel Prize. The upsilon, that's the discovery of the bottom quark, that's also a Nobel Prize. The Z is also a Nobel Prize. And you see the same thing in muons. All these particles can, and even more, can decay to muons. Actually, it's not true that even more can decay to muons. It's just that the muons have better resolution at low mass, down here by 1. So you can actually see these guys where you can't really see them in the electron channel. So basically, by seeing all of these guys, you can then, if you start to see another peak down here, and you look in your book and you say no particle there, then you know you found something, because you know you can find the particles that you should be able to see. You can also convert those into measurements. So here's a series of 6 measurements related to the Z and W bosons. And what they plotted here, you can't really see it, okay, is the ratio of the measured value versus the theoretical value. And you can see they all line up quite close to 1. Within their error bars, they're all consistent with 1. So that tells you that you're measuring what the theory tells you should measure. For the particles where the theory describes them well. You can also use jets of particles. And so here again is the jet momentum spectrum, and it goes over like 10 orders of magnitude. It's all divided up into different regions of the detector. The only thing to take away from this is the red line is the theory and the dots are the data. And you can see that it lines up quite well. You can even turn this into searching for new physics, actually. So you can actually take pairs of jets and make the di-jet mass, like you made the di-electron or di-muon mass. And a deviation from this would indicate, say, an excited quark. So you make this ratio, again, theory versus data, and you see that all the data sort of clusters around 1 pretty well. You'd see a big excursion at some mass, according to the new particle mass, if you saw something. So here you can set a limit on the minimum mass something must have in order for us to miss it, basically. So we're on the precipice of sensitivity for new physics, right? We have new results on quark compositeness, leptons that actually have color charge. I told you the difference between leptons and quarks is that leptons don't behave in the strong interaction, but maybe there's some weird lepton that does. Heavy W's and Z's. So again, here's the dimuon mass. This is the spectrum I showed you before, but focused at the very high end of the mass range. And the solid things are the backgrounds you expect. The peak here is, of course, the Z itself. If you had a heavy Z that was something like 8 or 9 times heavier than the standard Z, you'd get a curve that looks like this. And you can see the data clearly do not show you anything out here. So again, you can set a limit on whether we see heavier cousins of the W's or Z's. Similarly, we can look for long-lived stable particles that haven't been seen before. We can look for 4th-generation quarks. We've looked for large extra dimensions. We've even looked for microscopic black holes. And we've searched supersymmetry. Supersymmetry is one of those things where you have lots of parameters to turn. So how you search is you fix a bunch of parameters, and then you plot what's allowed and what's not allowed in 2-dimensional parameter space. So the solid stuff here has all been disallowed by previous experiments, and here's our limit here. So we are starting to push into new ground, even in supersymmetry. All our limits are competitive. They're either equal to or even a little bit better than pre-existing best limits on these sorts of processes. The unfortunate thing is we have no new discoveries yet. All right, so what about the Higgs? So the current situation is this complicated plot here. This is the hypothetical Higgs mass, and this is the limit at which you're 95% confident there is no Higgs there. So the data is this black line here. When this black line goes below 1, then you can rule out that there is a Higgs mass there, or a Higgs boson with that mass, which is like 158 to 175, at the 95% confidence level, right? So this all comes from the tevatron. We know the Higgs is bigger than 114, and there's this little window here that the tevatron has ruled out. That's the current situation. We don't have, at the LHC, nobody has a Higgs limit yet. So what we do have are projections of how we might do next year. So there's various projections here depending on how much data you get and at what energy you get. These are all being discussed this week, whether we get 20 times the data, 40 times the data, 100 times the data, and this is 40 and 100 times the data at a higher energy. But the same exclusion plot. So when the line crosses 1, you rule out that mass. When it goes below 1, here's their exclusion. You can see even at the most pessimistic, we'll extend the exclusion down here towards 130 GeV, and the exclusion goes all the way up here to about 450. With more optimistic scenarios, of course, the exclusion gets even better. It's harder to discover something than it is to exclude something because you need more events. So for discovery, the situation is a little bit worse. Usually when you have a 3 sigma significance of observation, you call it an observation. If it's 5 sigma, you'd call it a discovery. So you can see here's the most pessimistic prediction. We could have an observation in this range, although some of it is already ruled out by these guys, right? And the most optimistic thing, we would have a discovery if the Higgs mass lies between, say, 140 and somewhere out here at 280, and then also a window out here as well. So even with next year's data, we should be well into the Higgs hunt. That's the message there. But we shall see. So I hope I convinced you that the LHC is a fertile field to find something new and hopefully unexpected. The accelerator is back and basically with both barrels blazing. Our complex experiments are harvesting the data. In 2010, we've rediscovered the standard model. So we're confident that we could confidently have something to say. And we're also scratching the surface of new physics. So at this point, we just need to turn back on. We expect to do that in about mid-March. So stay tuned. Thank you for your attention. And I think there's time for questions. There's a microphone over there.